Hi, folks. Welcome to Lecture 31 in this Introduction to Proof series based on the book A General Introduction to the Art of Mathematics. I'm Joe Fields. Today we're going to be going through section 6.3 about proving things are equivalence relations. The plan is to say actually some introductory remarks, then see really why we bother with equivalence relations. In a sense, the raison d'etre of an equivalence relation is to create equivalence classes. And what are equivalence classes? Well, we'll see shortly, but the big point of them is that they give us partitions of spaces. So we develop equivalence relations, we get for free from an equivalence relation, we get these classes, and those give us partitions, and those are very handy in proving things. So I think I alluded to this before, there's a lot of machinery that comes to bear once you've shown something is an equivalence relation, or also true for ordering relations, just different machinery. Let's get going on this. A good way to think about what an equivalence relation is it's kind of like equals, but it's a light version of equals. We don't necessarily mean things are literally equal, but with respect to some standard, they can be thought of as equal. So equivalence is a lighter version of equals. Usually some feature gets highlighted a lot, and then other features get lost. Like, for instance, the idea that things may not literally be equal, but they do share some property. A good example to think about is the mod relations, the equivalence mod n. What gets highlighted is what your remainder is when you get divided by n, and what gets lost is your literal identity. We know that, for instance, 17 and 7, they're both 2 mod 5. So those will be thought of as equivalent, but clearly they're not equal. So the thing that gets highlighted is remainder. What gets lost is actual identity. A silly example. I am really into like the maker movement. I have a lot of tools, and my living room is actually a workshop, and I have probably more than dozens. I bet I have 50 different screwdrivers. None of them are equal. And there's always slightly different uses, although some of them I actually have dupes. But if you just need something for poking, they all become equivalent, right? They're just equally good at pushing something. If you need them to actually turn a screw of a different design, then they're not equivalent. So here's the official definition. We've seen it before, actually. A relation R on a set S. This is the homogeneous type of relation, right? Where we're working on a set, not going from one set to another. It's an equivalence relation if it is reflexive, symmetric, and transitive. Got to have all three of those properties. So let's go with an example of the kind of one I just highlighted, the equivalence mod 3. Two things are the same mod 3, and this is how we write that, a triple bar equal sign with a little 3 subscript on it. This relation is defined by x is equivalent mod 3 to y if and only if x mod 3 is equal to y mod 3. In other words, reduce them both mod 3, check if those things are equal, and if they are, then you write this weird symbol in between them. Proving that this is reflexive, symmetric, and transitive is super easy because of the way it was defined. The biconditional here that defines it has an actual equality on one side. So we're using actual equals there, and that is reflexive, symmetric, and transitive. So we almost automatically get that the equivalence mod 3 is there. In more advanced work, you would say something to that effect. You would say this is clearly an equivalence relation since it's defined in terms of equality, and it inherits the properties it needs to from equality. But we're gonna do this the hard way. Right? We're gonna actually write it all out, just because we're not at the advanced level yet. So you should see what it's like to write a proof that something is indeed an equivalence relation. All right, so we'll start off with the the formal theorem statement, which is pretty easy. We're just claiming that equivalence mod 3 is an equivalence relation. The fact that I call it equivalence mod 3 is sort of foreshadowing that indeed it is an equivalence relation. Maybe it would have been better to just use a generic R there rather than the usual symbol, but here we're stuck with it now. All right, how does this proof work? Well, as we've done in the past, you start off by marking your proof off with the word proof to indicate to people that you're doing some formal argumentation. And I like a we need to show sentence up front in my proof. So, but of course, this is if you're at anything beyond just the bare beginner level, everybody knows that if you're showing it's an equivalence relation, you're going to verify these three properties. It's kind of useful to note that the domain of this set of this relation rather is the integers. It didn't say that in the build up to what we've done here, but that is the correct domain. So a proof like this is almost always just going to be an itemized list, and I like to label my items with the actual property name. So we'll have an item that's called reflexive. What are we doing in there? Well, first we suppose we've got a single universally quantified variable, right? So suppose we have a single arbitrary integer, calling it x. Since x mod 3 is equal to x mod 3, that's silly, but it's what we need. That's the reflexive property of equality. It follows from the definition that x is equivalent mod 3 to x. Thus, equivalence mod 3 is reflexive. Okay. The next bulleted item in our thing is we're going to verify that symmetry is that this relation has the symmetry property, or that it is symmetric. So here we're going to need two universally quantified variables. So we begin with saying, suppose that x and y are arbitrary integers. And now inside of this, you can think of each of these bullets that we're doing as a little mini proof inside of the big proof. So I've got a we need to show sentence inside of here. We need to show that if x is equivalent mod 3 to y, then y is equivalent mod 3 to x. So I'm going to throw in the extra stuff we get. Remember, this is a proof of a UCS, a universal conditional sentence. So we add in that the variables satisfy the antecedent of that UCS. Okay. So we've got an additional assumption that x is equivalent mod 3 to y. Sorry, I was scanning my own work and trying to find the spot there. Let's do it there. Okay, so where do we proceed from there? Well, by the definition, it follows that x mod 3 is equal to y mod 3. Great. Now we use the symmetry property of equality, and it says so right up there. By the symmetric property of equality, we know that y mod 3 is equal to x mod 3. And from that, it follows that y is our new relation to x. That is, y is equivalent mod 3 to x. Thus, since we did this arbitrarily for no real presumptions about what x and y are, other than that they are equivalent mod 3, that they're equivalent mod 3 in that one order, x to y. Anyway, we showed that it's also equivalent mod 3 in the other order, and thus that equivalence is a symmetric function, relation. This proof got a little long, so I had to bump it onto the next page. Transitive. So three variables we need to have for that. Suppose x, y, and z are arbitrary integers. Again, a little mini we need to show. What is it we need to show? That if x is equivalent to y and y is equivalent to z, we should get that x is equivalent to z. So we make the further assumptions in the antecedent of our UCS there, that x is indeed equivalent to y and y is indeed equivalent to z. I'm using a little shorthand saying equivalent rather than equivalent mod 3, just because that's a little long-winded. So what does that get us? Well, that x and y are equivalent, it lets us write down this equality that x mod 3 and y mod 3 are the same. Similarly, since y and z are equivalent, we get this equality that y mod 3 and z mod 3 are the same. And now those pairs, that pair of equalities is involving x mod 3, y mod 3, y mod 3 again, and z mod 3. And y mod 3 is the thing that's in common between the two things. The transitive property of equality lets us deduce that x mod 3 and z mod 3 have to be the same. Have to be the same. And from that, we deduce that, well, x is equivalent mod 3 to z. Thus, since we work generically, equivalence mod 3 is transitive. There should generally in this kind of thing be a wrap-up sentence. So after the bulleted list of showing the different properties, just wrap it up and say, okay, we've shown that this thing is reflexive, symmetric, and transitive. We've proved it's an equivalence relation, QED. Okay, equivalence classes. This is actually what we are after in the idea of getting handy with equivalence relations, is to be able to understand equivalence classes. So I was talking about my tool collection before. My screwdrivers would all end up in the poking devices equivalence class. If I have a lot of hammers too, from great giant ones to really tiny little things that are meant for precise work. But, all my hammers end up in the smashing devices category. I've got tools that are for squishing things, vices, and various kinds of pliers. So I guess there's a squishing devices category or class. But, these things are not literally equal to each other. They're just considered equivalent if you have some function in mind for them. Function not in the math sense, but in the mechanics sense. So what about the example we just did? In the equivalence mod 3 example, there is an equivalence class for each possible remainder, mod 3. And this is how we generally denote these kinds of things. Take an element and put a bar over it, and that represents all the things that are equivalent to, the ones I've used are 0, 1, and 2. So the equivalence class of 0 with a bar in it over it, is I'm just noticing that I'm slightly off in this because that relation is defined over the integers. So I should have 0 plus or minus 3 plus or minus 6 plus or minus 9. Okay, well, for the moment, just think we're working over the naturals, and then these are fine. 1 bar would be 1, 4, 7, 10. These are the things that are 1 mod 3. They're 1 greater than an even multiple of 3. I probably shouldn't have used the word even just now, because I don't mean even that way, but I mean even, and that it's a multiple of 3. Just say it that way. And then the things that leave a remainder of 2 when you divide them by 3, that's 2 bar. Okay, so the classes are the things, they consist of all the things that can be treated as if they were equal, but not really equivalent, because they're equivalent under the relation. So here's the formal definition. Given an equivalence relation R on a set S, and an element of that set, calling it X, the equivalence class of X is all the things in the set, so that, and we're calling the things we're looking at Y's, Y needs to be related to X. Now, since this is an equivalence relation, I could just as well have written X is related to Y, because we do have the symmetry property. That set is denoted multiple ways. Oh yeah, this is a good point though. Notice that at a minimum, the equivalence class of X will contain X itself, so it's guaranteed to be non-empty. Do you see why? Well, we have the reflexive property, so X is guaranteed to be related to itself, and that means it will satisfy the membership criterion for this set. So yeah, X will be in that set. I just said why. There is not a fixed notation for it. for these ideas. I do think X bar is the kind of thing you'll see very often, but you will also see what looks like a division thing. it's it's actually read as X mod R because it's very much like the modulo relationship that we have previously studied. So X mod R or X bar, those are popular choices for the equivalence class containing X. Really got to make sure that you get the distinction though. X bar is not the value X. It's an entire set of things usually. At a minimum, it's a set that contains X, so it's a different type than X itself. Just to make you really, I guess I'm beating a dead horse here, but you can say X is an element of S, but X bar, you have to say it's a subset of S. Okay, so every element of S will define an equivalence class. This is true. But every element of an equivalence class defines the very same equivalence class. So maybe we should somehow make a standardized choice. If you want to, important point. I had that new notation for the equivalence class, X mod R. This is read as S mod R. And that's the entire collection of all these sets that you get as equivalence classes. For example, if we're doing the mod 3 equivalence on the integers, there are 3 equivalence classes. There's some wiggle room, I like that phrase, concerning what we call them. You could say Z modulo equivalence mod 3 is the set with the 3 equivalence class possibilities, 0 bar, 1 bar, and 2 bar. You could also, though, say Z mod equivalence mod 3 is -1 bar, 0 bar, and 1 bar. These are both great choices. There's plenty of other choices, but if you're going to pick representatives for the equivalence class, and that's what the 0, 1, and 2 in here, or the -1, 0, and 1 in there are, it makes sense to pick them small, near the origin. Here, the choice has been made to use 0 and the smallest possible positive numbers that are in the 3 equivalence classes. Here, the choice has been made to keep the absolute value of them smaller, which is often reasonable. Anyway, those are both ways of referring to the same collection of sets within the integers. Yeah, the difference between these ones, they both have 0 bar and 1 bar in them. You need to see that 2 bar and -1 bar actually are the same set. They're all the things that have a remainder of 2 when you divide it by 3, because -1 is 2 greater than -3. All right, well, that leads us to the final piece here, partitions. And partitions are, in a certain sense, the reason for doing all this. I'm going to use equivalence mod 5 to give you a nice example. Here's the equivalence classes. I've made the small positive equivalence class representatives choice here. 0 bar that's all the things that are literally multiples of 5. 1 bar is the things that are 1 bigger than a multiple of 5. So -9, -4, 1, 6, 11. 2 bar, it's always hard to see that the negative things are right, but -8 is 2 greater than -10. And -3 is 2 greater than -5. I think the rest of the positive numbers are clearer. 2 is 2 greater than 0, 7 is 2 greater than 5, 12 is 2 greater than 10. Yeah. By the way, if you kind of look at this collection in columns, you'll see, you see how you go down this column, 0, 1, 2, 3, 4, and then jump back to the top, and you see 5, 6, 7, 8, 9, then jump back to the top again, 10, 11. Am I convincing you that everybody's in one of these equivalence classes? Well, that's the thing I was trying to convince you of. Every integer is somewhere in those equivalence classes. I just was sort of looking at the positive ones, but it's true in the negative territory too. -1, -2, -3, -4, -5, -6, -7, -8. You see, you're going to get them all. Also, there is no overlap between them. If two things were in the same equivalence class, that would mean they had two different values, mod 5. And, that's not how mod 5 works. You get a unique answer from the mod function. Okay, so what is a partition? It's basically taking those two properties that we just saw and formalizing it. A partition of a set S is a set P consisting of subsets of S. So we're breaking S up into a finite number. Well, it doesn't need to be finite, frankly. Some number of subsets. And what we need are two things. S is literally the union of all the things that are in P. So every element of S is in one of those X's, one of the elements of P. And what the heck? This seems complicated, but it's not really. We've got a universal thing, universally quantified over sets. This is because they're elements of P, and P consists of sets. For every pair of sets in P, if they're distinct, then I know that their intersection is the empty set. In other words, distinct sets in P have distinct elements. They're disjoint from one another. That's the correct phrase. So the union of all the things in P gives you all of S, and every pair of different things in P are disjoint from one another. So let's see. Did we look at this relation previously? I feel like we do. The relation S on R. Well, maybe we haven't, but still, we can look at it now. The relation S on the real numbers, which we used to say that two numbers have the same sign. How does that look? Well, if they have the same sign, they're either both positive or they're both negative, or if they have no sign, they're zero. And that means the equivalence classes for this relation are the positive real numbers, the negative real numbers, and the singleton set with zero in it. That partition is so important, it's got its own name. It's called the trichotomy property. The real numbers can be partitioned into these three mutually exclusive cases. And that's actually a very, well, we used it back in chapter 3 when we were doing our sort of intro to writing proofs. The trichotomy property is one of the things you can use to introduce a proof by cases, right? If you have to prove something about a real number and you don't know where to get started, think about applying a trichotomy. You can guarantee that every real number is either positive or negative or zero. And so maybe that further assumption gives you enough ammunition to get rolling on your proof. I'm going to do another example. We're beginning to move towards this section on combinatorial proof, and so it's time for us to really get a little bit more hardcore about graphs, which are not the y equals x squared kind of graphs. This is a discrete math version of use of the same word. There are mathematical models for things where you have things and connection between those things. So relations are an example of a thing that is modeled very nicely by graphs. We actually talked about the digraph of a relation previously. So what is a graph more formally? A graph consists of actually three things. Two sets, V and E. They have those particularly odd choices of letters because V stands for vertices and E stands for edges. So the vertices are the things and the edges are the connections between the things. There's also a relation that relates the edges to the vertices. It's a relation that connects edges to pairs of vertices, actually. Well, it can be a single vertice. Actually, there's some choices here. We can send an edge to an ordered pair of vertices. That's the digraph situation. We can send an edge to an unordered pair of vertices. That's the usual case. We just think about a connection with no idea about whether there's a direction to it or not. We can even well, we can allow for the possibility of repetition. So an edge may have the same vertex at both of its ends. That's what a loop is when we looked at that in talking about the digraphs of a relation. Anyway, so we'll have a vertex set that consists of two things, A, B. Just giving you a quick example. An edge set that consists of one thing. And here I'm spelling out the edge endpoint relation. E is related to A and E is related to B. I can't tell you whether that's a directed graph or an undirected graph. I guess I would sort of need to have the direction implicit in there if I was trying to get the directed thing. So let's assume that's an undirected one. But E has A at one end and it has B at the other end. What are we talking about there? I, I feel like that's a really crazily complicated way to represent something that's super easy. You've got two vertices, label them A and B. You've got a single edge that connects them. That's labeled B. So we're just talking about a little bar with a point on either end of it. That's what has been defined here. But that's baby steps, right? You can take that representation of listing all the vertices and all the edges and how everything's related, and take it quite a bit farther. Yeah, that sure was. Okay, so an example of equivalence, but not necessarily equality, is graph isomorphism. Two graphs are isomorphic when there is a mapping that takes the vertices of one graph to the vertices of another, takes the edges of one graph to the edges of the other, and we use the term preserves here. It preserves the edge endpoint relation. It's much easier said than done. Oh, let me point out the etymology. Sure, isomorphic. Iso is I believe that's Greek prefix that means equal, and morph. Well, you've probably heard about like images being morphed. Morph really means shape. So isomorphic means having equal shapes. Uh, Having equal shapes determines a set of equivalence classes. Now, I haven't really been very accurate in what this isomorphism business is. I just told you it's easier said than done. Um, maybe I should be a little more careful. Now I'm gonna do this in the light way first, and we'll come back to graph isomorphism in a later chapter. So that's okay. But we've got some of our isomorphism classes, or I think I still like to call them equivalence classes right now, that have names: Kn, Cn, Pn, and Wn. I wrote a note to myself that I should draw pictures. Well, let me tell you what Kn is first. The German word for complete starts with a K. So uh, K2 is actually the graph we just talked about. It's got two nodes in it, two vertices. Oh, yeah, I think I didn't mention that, but nodes is another way to refer to the vertices. They're synonyms. So sometimes you hear me say nodes, sometimes vertices. K2 is two nodes and a single edge between them. It's complete in this following sense: every edge that could be there is there. So let's think about what K3 would look like. Well, that's going to have three nodes. And as I said, every edge that could be there is there. Now, I kind of said that in a strange way because it's not quite true, right? If I wanted to, I could throw more and more edges in here. I could put a whole bunch of parallel edges into this graph, and that's fine. But what I'm dealing with right now is a category known as simple graphs, where an edge either exists or it doesn't exist. Usually, not always, usually the road systems is a simple graph. We build a highway between two cities and then go, hey, let's build another highway between those two cities. Well, actually, I used to work in Washington, D.C. and lived in Baltimore, and there are two major highways that go between those two. But it is a pretty rare case, right? So most often you have single connections. That makes a graph simple. I'm going to show you two different ways to draw K4. One of which is, okay, drop 4 points on the page. and then make every connection you possibly could between things, but only one of, of the possibilities. That's a way to draw K4. Um, some people might prefer to draw it without having that place where you cross, and you can do that in this case. If you put one in the middle and put three others sort of outside it, off the screen. In that case, you can make connections between all of those three outside ones, and then have all of them connect to the guy in the middle. And so none of our edges are needing to cross over one another as they did in this picture. That's actually probably the first non-trivial example of graph isomorphism. These are two distinct pictures, but in terms of having the same shape, they really are the same. I can't quite do this with a static picture, but on a computer application, you can make these dots and make these connections and then move the dots and see that you could just slide this guy over to here and maybe slide this one over that one. It just change the positions of them while maintaining those lines in between them, and take this picture and morph it into this picture, or vice versa. The other, so that's a nice example of an equivalence class, the class of complete graphs. There's also CN, PN, and WN. Those are cycles, paths, and wheels. I'll just give you maybe a couple of quick examples. C5, for instance, would be 5 points that are connected like this. But I could also have 5 points that are connected like this. If you watched me as I drew that, though, you'll see that that star is really the same thing as the C5. The connections went around in a loop and came back to where it started. So those are two different graphs, but they are really the same in terms of their shape. That's the equivalence class C5. P5 is even more boring. It's a path of length 5. It just goes from one spot to another, and there's 5 dots in it. But again, you could have paths of length 5 that don't look like they're just such a simple thing. Did I get the right number? 1, 2, 3, 4, 5. Oh, I shouldn't have done that last one. You see what I'm saying here? That those have the same shape. If you're free to move things around a little bit, you could unravel that scramble and turn it into a straight path. And wheels, I'll give you an example of a wheel. This one's a wheel. That one would be called W3. It basically has an axle and then a cycle around it. So it's a combination of a cycle with somebody centered. If I put a dot in the middle of this and connected everybody to that dot, now I have 6 nodes, but it's still called W5. And that's probably enough for us to see the various equivalence classes you get by thinking about isomorphism as an equivalence relation on the set of all graphs. Cool. That brings us to sort of an interesting ending point. But we'll, because I give you this final example without showing you that it's an equivalence relation. I just claimed it was. Can we quickly just see that that it really is? Does it have the 3 properties? Reflexive. Is a graph got the same shape as itself? Can there be a mapping that sends the vertices of a graph to itself, to its own set of vertices, the edges of the graph to itself? Yeah, the identity mapping. And the identity mapping is certainly going to be respectful of the edge endpoint relation. So sure, reflexive is easy. Symmetric. If I've got a mapping that sends the vertices and edges of one graph to another, can I come up with a mapping that does the opposite job, sending the second one back to the first? Yeah, that's the inverse mapping. And so what you see is this mapping needs to be bijective. It has to be a function that's one-to-one and onto. Finally, transitivity. Well, that's saying that if 2 things are equal, are isomorphic, And then the second one and a third thing are isomorphic. Can you get an isomorphism between the first one and the third thing? And what you do is compose the mappings. So yes, you can. Isomorphism has all three properties. I suspect that could stand a more formal write-up at some point, but this is good for now. Okay, that is truly the end of what we need to discuss about equivalence classes and equivalence relations. If you're so inclined, I think it's a great idea to go back and read this section again. And then if you're planning to move ahead, take a peek at section 6.4 before you proceed to lecture 32. Have a great rest of your day.